Hey, hi everyone. Welcome to Research Jam Session 1 of Genloop. Research Jam is a recent initiative at Genloop to build a research community where we are openly engaging and discussing the latest research and latest developments in the Gen AI world, particularly in the LLM world. And this is our first session. Let me quickly share my screen and walk you through the agenda first. Right. So I'll be presenting some slides to cover the paper SWE-RL. SWE-RL is a recent paper from Meta. It was around 3 weeks back. It was the top paper of the week around 3 weeks back on the LLM Research Hub. More details in the following slides. And it was about applying reinforcement learning based reasoning to real world software engineering. So they had a software engineering problem. They created a data set of GitHub issues, the code context, and the patches that were done, and used that with a very creative reward modeling process to train a Llama 370 billion to understand reasoning and how to do software engineering tasks. Now, we wouldn't say they were perfect, though their scores on benchmarks were very good, they were giving themselves a lot of the leg room by doing generating many variations of the answers and taking the most repeated answers and then considering that as the candidate to actually solve a feasible approach. But still, I would say a lot of uh, ground has to be covered. But nevertheless, it was a very interesting application of GRPO, the one that DeepSeek pioneered. A very interesting application of GRPO to this problem, and showed that just by having this kind of a data set and with a reinforcement learning based technique, you don't need humongous amount of labeled tasks and generate reasoning, and even that reasoning could be helpful for other domains like general answering and anything that requires any reasoning. So we'll keep the session interactive. So if anyone has any things to ask, any points to discuss, happy to please feel free to interrupt and bring your point forward. So, quick thing, just setting up the context for this research jam. We are building Genloop. We help enterprises build domain intelligence seamlessly in a three-step process. Uh, we integrate with their enterprise data, automate the entire LLM development cycle, which is about integrating with that data, refining that, training and evaluating multiple models, monitoring those models, and the biggest asset is continuous learning that we have added to our framework. And finally, you get LLMs that you can have in your applications with unmatched cost control and performance benefits. And we've seen many enterprises leverage our tech to build Gen AI for production use cases and get much better accuracies than public LLMs were giving them. Much better control, like reduction in hallucinations, improvement in accuracy, flexible hostings. They could host it on-prem as well, and a lot better cost at scale. So this was an LLM that they could own or they could host in a flexible environment, so they don't need to pay rent per intelligence. And a lot of our work was around, being at the forefront of tech, trying to understand what is the best and the latest that has been happening, and go deeper into using that and applying it to the problem that we are solving, which is about customizing LLMs for enterprises and building their domain intelligence. So we had built an internal agent which could collect and source the top papers of the week, and of course, we all um, understand right now how fast the Gen AI space is evolving and running. So therefore, we had an agent that could go through and source multiple papers, and we were picking or ranking the top papers in terms of the relevance, the quality of the paper, the quality of the research that was in the paper, the popularity it was having, the adoption it was having, and the impact that it could have. And those are the ones that we were using to, keeping ourselves updated. And we thought, like, why not just build a tool so that everyone else could also benefit from it? Because, anyways, we had a lot of conversations where people were struggling to find what is the best and the top research happening in this space. So we built that, and you can access this at Genloop.ai Research Hub. It was very well received by the community. First of all, thanks for that. Um, After having released it, there was a request from certain folks in the community to also have a discussion group on it. And that is where we have institutionalized the Genloop Research Jam. So, Genloop Research Jam is basically a very selective space for folks to gather and discuss about the Gen AI research periodically. This is the first research jam, and as I said, this is about the SWE-RL paper, but we'll make it very periodic and make sure that it is happening at very frequent intervals. Cool. Um, so first, the paper. SWE-RL, as I said, is about applying GRPO-based reinforcement learning on Llama 70B, 3.3 Llama 70B to develop code reasoning. And this diagram basically summarizes the entire architecture of how they're doing things. So the overview is that, first of all, they take GitHub and GitHub archives to get a raw PR data set, which is basically, the discussions, etc., that has happened on a particular PR, the code context that is available for that, and the final patch that was proposed for it. So with the issues, etc., you understand what was the problem. With the code context, you understand what were the related files, etc. And with the applied patch, you understand what was the final solution that was there. And from that, they prepare a seed RL data set of issue, code, and patch. Now, what they want to develop through that is they have the ground truth, basically the Oracle patch, and they want an LLM or a language model to develop the reasoning and be able to create that patch by itself. So it's a very creative use of existing data set without having to invest heavily into creating one. So the pipeline at test time was that an issue and code would be given to an LLM, and it had to give the final patch based on reasoning. And therefore, the training path and the training time, the architecture was that when the LLM gives the reasoning, if it is giving a wrong format, for example, if it is not giving the thinking tokens, you penalize it. A score of -1, and you give it to the GRPO. GRPO is basically the RL algorithm that we're using to optimize the weights of the LM to achieve the objective. And when it is able to give things in the right format, it proposes a patch. The predicted patch and the Oracle patches are compared, and the final reward or the score in a 0 to 1 range is then given to the GRPO for further optimizing. So if the LM is able to reason well and give the exact patch as the Oracle, it will get a score of 1. If not so, it will get a score of 0, and therefore has to reason better. That is the same thing as DeepSeek was trying to do. And the idea is that having to do it, the model uh, in a few iterations arrives at the aha moment where it is able to develop the reasoning on how to solve the problems. And of course, that instruct Llama model is the base where the reasoning starts. Uh, One small point though is the compare function that they're using here is PyTorch def-lib sequence match. So basically they're just doing a sequence match here. So I wouldn't say the compare function is the best one to give the reward, but still a good start. So in code, like we know, semantic similarity is important. Like one code could be uh, not exactly the same, not exactly matching the Oracle patch, but might be a better uh, an abridged version of it, or a better version of it, or maybe just a minorly different version of it, but achieving the same objective. So this one would penalize for that as well. So we are in a way constraining the LLM to reason only in the way that the Oracle has done. Any questions so far? Anything before we go further into the key takeaways and reward model? So the key takeaways of the paper are that first, it's reinforcement learning for software reasoning. The first time that this was done and achieved very comparable results. So through this approach, the authors have shown that the LLM learns debugging, patching, and evolving software autonomously, mimicking seasoned engineers. So much more robust than the normal techniques that we have tried so far. Second is state-of-the-art performance. They solve around 45% of issues on SWE bench, which is a benchmark for software engineering tasks, performing on par with much larger proprietary models like GPT-4o and the best among less than 100 billion parameter models. And one of the interesting takeaways was that it generalized reasoning as a byproduct. So basically, the developed model outperforms supervised fine-tuned baselines on out-of-domain tasks like question answering, etc. So therefore, the reasoning that it has developed for coding was able to give them a value add in other domains as well. So, pretty portable in terms of the reasoning that has been developed.
Quick question, Ayush. So, what kind of domains are we talking about here? Question
Yeah,
answering
so
and
there is general MMLU benchmark. There
uh-huh.
is, of course, code-based benchmarks like human eval, library-based coding like Big Code Bench, code reasoning like Crux eval, and then math. So basically, they tried to benchmark on two other tests, which is like math-based and general-based, and they saw that with this RL-based training, they were able to do even better than the instruct model on certain cases or retain the accuracy in others. Actually, in MMLU and math, it improved over the instruct model without having any data set exposure to math based or general reasoning tasks.
Okay, thank you.
Cool. So, how are they setting up the entire system? First of all, from the training perspective or from the test type perspective. So, the prompt to the system is simple, that a user will ask you to solve a task. You should first draft a thinking process inside the thinking tokens and then generate the solution. And your response format must follow the template below. So you should give the thinking token inside the think tags and then give your solution. The user would give the issue, basically maybe the GitHub issue and supporting text that highlights what is the problem that they are facing, the code context, which are supporting files or things that are able to give the context of how the code has to be changed, and uh, replace or basically any edits to fix the issue or any instructions to fix the issues. And the assistant would then go on and generate the reasoning inside the thinking tokens and the solution. That is how the instruction to the LLM is. The reward function for it is basically a -1 if the format is wrong, as we were seeing in the diagram, and compare base score, which is in 0 to 1 range of patch that is predicted and patch, which is the ground truth. The patch in the ground truth is basically what we have uh, refined and curated from the GitHub code database that we have. So the reward model is -1 to 0 to 1, like generally from the compare one, and -1 if if the format is wrong. And the GRPO objective that we are trying to maximize is we are maximizing the expectation uh, in terms of we're trying to first maximizing the probability of the new policy such that it generates that token given the context that is given the maximum reward, and we are applying a clip on that. So basically, what we're trying to make sure is that the training is happening we are ensuring a stable training in the range of 1 plus epsilon to 1 minus epsilon. And then we're also making sure that it does not, the new policy or the updated policy does not diverge too much from the reference policy. So therefore, we also are applying a KL divergence penalty. So it's standard GRPO objective. It's the same thing that they're doing there. It's just that the data set is different, the policies are different, so the context is different. So the Q here would be the prompt as we were uh, just going over. And the output here would be the tokens of solution and thinking and thought processes that are generated.
Okay. So I can possibly add a little bit on this.
So,
The pi theta is basically the new policy, and the pi theta old is the older policy. Now,
right.
that is being multiplied by this AI, which is basically called as the reward function. So, what happens is that for a particular context, we are basically generating G different groups of samples, and we compute reward for each of them. And then we basically normalize them to have values between 0 and 1. And basically the mean becomes 0. So what it means that uh, on an average, there will be some generations which will have negative reward, while some generations will have positive reward. And if we look at it, so wherever AI is positive, in that case, pi theta by pi old will basically move towards pi theta, which is the new policy. So essentially, this is the intuition behind it, that for positive rewards, we are basically trying to move towards the new policy. And wherever AI is negative, in that case, we move away from the newer policy. So that is how basically this is training. And in order to make sure that uh, the difference, the policy update is not too huge, we basically clip this pi theta by pi theta old at some particular threshold. And then there is the scale divergence term, which, as Ayush mentioned, ensures that the new policy is not significantly deviating from the original one, from the base one.
Right, right.
Yeah.
So thanks, Sachin. Actually, one interesting point of discussion here is what should have been what could have been a better reward function. Like, of course, we discussed that the compare between the predicted patch and the ground truth patch is sequence match, and that is definitely not optimal for the problem because,
Yeah.
as we were discussing,
Yeah.
one code could be written in a different way but have the exact same semantics and the exact same O1 and
Correct.
space and time complexity.
Yes.
So, what could have been a better reward function here?
Um, for code particularly, uh, so one way of thinking uh, about this can be that the eventual uh, code output that was uh, there before applying the patch and after the ground truth patch and the predicted patch, if they are resulting in the same output under different situations, that should also be given a positive response, reward despite their sequences not exactly matching. So that basically the comparison is happening at a more semantic level rather than just comparing the base sequences. And again, I believe that this particular reward function will vary significantly based on the problem that we are targeting at hand. So
Hmm.
this is the thing which can actually be controlled by the developer uh, in ensuring how the training should go about.
Hmm. For sure. But if we go more concrete, like for example, one is we could have used an LLM as a judge to give a reward between 0 and 1, like assuming little bias or no narcissistic bias by the LLM um, to favor a certain kind of generation. But we could have given them the predicted patch and the ground truth patch and like ask them, like, do you think both of them are exactly same? Or do you think both of them are different? Or maybe give some parameters on how to compare.
That's a good
So
point. Yes.
that is the one function that comes to my mind that could be better and I would not say robust, but in terms of comprehensiveness of covering the comparison, that could be better. Of course, given that you are, you know, uh, controlling the LLM and instructing the LLM in a proper manner so that it does not digress from the comparison. The second could be something related to execution. Now, it's difficult to frame here, but if you're able to execute the predicted patch and the ground truth patch, and if there is a unit test available, now the problem is that it's not always possible to have a unit test
Yes, that's right.
covered to a
Mm.
patch. But if you could have a result value, for example, with text to SQL, that is a very good reward function with whether the SQL query executed or not. So maybe a binary answer on a successful result or a unsuccessful result would also be a good function here. And third thing that comes to mind is basically those semantic scorings. LLM as a judge also takes care of a bit of like quite much of that. But if you don't want to go with LLMs, possibly some kind of line by line semantic score and then averaging on that, uh, or line by line code comparison and averaging on that. I'm not sure. Line by line could be wrong because you have to look at the code from the
Mhm.
in a distributed fashion. But maybe some kind of a better comparison rather than just a sequence match. What do you think?
Yep, that makes sense. And also, the reward function need not be unidimensional, right? So, it can consist of many of these components put together, uh, and
Right, right,
weighted also. And maybe
right,
those weights also can be made learnable uh,
right.
to some extent. So, is this?
Learnable. So two points here. Like one
Huh?
is in our experiments with the reasoning based models, what we found was that when we created many reward functions, the model training became fragile. So having cleaner reward functions and minimal reward functions helped. Like, of course, that was just one set of experiments that we performed. One or
Yeah.
two sets of experiments that we performed. It's limited to generalize overall, but that was our personal experience. That we should have minimal reward functions. That was one point. Second is how do you propose to have a learnable parameter, learnable weights?
Okay. Uh, so I need to formulate it as such, but possibly by formulating it as a min-max optimization problem to some extent, that I
Mm, mm,
associate weights with each of the uh, reward component, and
mm,
then uh, I would maximize. I would like to maximize with respect to the absolute value of reward.
mm.
Uh, while minimizing the overall objective, which is basically the negative of. So yes, I think there is one issue in this equation. It should be negative of this expectation, right? Because ideally we are trying to maximize this part, this j of theta. So
Right, right,
we would want
right.
to
So
train.
it is.
Yeah,
This is about maximizing. So
yeah,
maximizing
okay.
this would mean that we are maximizing the reward and minimizing the tail
The
damages.
negative of it, yes. Okay. So I think
Say uh, one way to have a learnable weighted function. Let's say we have two more reward functions here.
mhm,
LLM as a judge is one, and then maybe some other execution score is there.
yeah.
One way could be like instead, like I'm a little skeptical about having a system that assigns weights on random. Like uh, uh, I'm skeptical about reward hacking, maybe, or
No,
um, unstable
it's not
learning
re-
there.
it's not exactly hacking per se. So where this thought is coming from is that uh, so which component of the reward function to give more emphasis to uh, should ideally be dependent on the sample, on the training sample, right? So in
Hmm.
some cases, it might be preferred that we give
Oh, right,
more emphasis to sequence matching. In some cases, we want to give more emphasis to the execution similarity, the
right.
sameness in the execution output. So something around that can be done, and constraints can be applied, right? So we can ensure
Right.
that. the sum of all the weights is equal to one.
Right. Right.
And
And if we
uh,
and and if we can have a human in the loop kind of a process, let me elaborate that maybe we start the training with certain weights. As the training is progressing, we have certain checkpoints, maybe at every 1,000 iterations or so, and we can, maybe have the option to tweak the weight and resume from that checkpoint. So,
I think
using some
absolutely.
observations in the past, uh, maybe we are seeing that, okay, it is getting very similar to the one that we are doing, but it is not executing. So you may assign a higher score on execution. Then with certain training, we see it's getting better at executing. It's
Yeah.
following the format, but it is getting too trained on the exact thing. Then we can
Yeah.
possibly reduce or increase the score for the semantic one and reduce the score for sequence match. Some kind of
Yeah.
that process would also be followed so that we are iteratively making the model reason and get better.
Absolutely. I mean, that's a good point. And I guess that will be much easier to start with because
Yeah,
the trainable weights can bring in training instabilities. I mean, that is
exactly,
something I guess will be uh, can be an active, can be an interesting area of research actually.
exactly.
Yes. Yeah.
Right. Yeah, but great conversation here. But of course, this was the
Okay.
reward and objective that they went with. Nothing bad. Like it was a good starting point. And this was their training and eval setup. Um, they the model, the base model, as we were saying, was Llama 3.370 billion instruct. They applied this SWE-RL, which is basically this entire overview that we were discussing for around 1,600 steps with a 16,000 context window. Um, and cursory details here, but the evaluation was around. This is the interesting part. So they generated 500 patches for each problem using a temperature of 1 and took the top 30 reproduction tests for execution and re-ranking. So basically, every example must have taken a lot of time for them, first of all. So if one reasoning and execution is taking around 30 seconds, 500 patches would have taken them 250 um, minutes. And then, so basically 4 hours on a problem, is it? Or am I going wrong somewhere in my maths?
Yeah, one thing I'm not able to understand clearly here is what do they mean by top 30 reproduction tests for execution?
What I
So
understood was that once they generated the patches, they are grouping them in similarity and they're taking the best one out of them and then doing a pass at one. We can actually go to the exact text and review.
yeah.
Okay. They evaluated on SWE bench verified. In the main evaluation, we generate 500 patches for each problem using a one temperature and use a top 30 reproduction tests for
For ex-
execution and re-ranking. Ultimately, only the highest ranked patch for each issue will be submitted for SWE bench evaluation to calculate the pass at one score.
Oh,
Top
okay.
30
Uh,
reproduction tests.
uh, I guess I kind of understand because again, if we if we relate it with the GRPO objective, basically
Hmm.
we are averaging over the number of groups, right? So
Right.
in this case becomes 500, and possibly they are picking up uh, uh, the predictions that have top 30 AI values or the reward function values.
But why they're calling it reproduction tests?
Let's-
Let me again freeze on that.
yeah.
In the main evaluation, we generate 500 patches for each problem using a one temperature. So this is pretty, I'm pretty sure
Yeah.
about that. This was to, have a mode kind of a generation,
Yes.
generate multiple
Agreed.
variations and then pick the best one. Now, how do
Yeah.
you pick the one, the best result? Uh, I would. Like if I were to do it instead of reading about how they did it, I would have basically grouped by similarity and basically converge on the prediction the model is giving the most and use that for pass at one score. That is how I was also inferring their line. Was not exactly clear to me. Do you
So
guys think?
when you're saying similarity based, you are essentially your similarity is nothing but your reward function value, right?
Right. It could be reward function or it could be the string grouped on the string that is getting generated as well. Like maybe um, I don't think that will be feasible for 500 examples, but of course, yeah, reward function wise, if it is same, it will have the exact reward. So how about you just group by the reward and mm, pick the one with the best reward, or maybe they had certain. I'm not sure. They're saying reproduction tests for execution and re-ranking. So did they have? Oh, possibly every SWE bench example has some reproduction tests. So
Okay.
every problem in SWE bench has some test or unit test or all these things available. So with the 500 patches, they ran the reproduction tests on the top 30 of the patches that were getting generated. Those top 30 could be from the reward model.
But then
And
here is the
for
question: why
that
do
top
they?
30, yeah.
Uh, okay, okay, I get it. So they're using a
So
relatively high temperature and
So
getting top
for
30.
500 patches, they would get ordered by the reward that they were getting generated. They
Yeah,
would pick the
yeah,
top 30. On those
yeah.
top 30, they would run the sweep bench reproduction test, or basically the unit tests that come with that, and then pick the highest ranked patch based on those unit tests. And that would go
Got
into the
it.
submission for sweep bench.
Got it. Yeah, that makes sense. Makes sense.
Right. Right. Cool, cool. And again, they were also comparing against Llama SFT and a base model and other proprietary models. So that was their training and eval setup. And one of the best uh, parts of the paper is this reflection, like DeepSeek's aha moment. They have their own aha moments, which is, like if you go over it when they were solving, the model would uh, do self-reflection, like, but wait, but then I saw it and
Yeah.
all that. It would explore alternatives, or a more Pythonic way of doing this would be this. Alternatively, we could do this. But the most straightforward way to do this is this. And sometimes also do a divide and conquer. For the first eclipse, let me do this. For the second eclipse, do this, and basically do some kind of a dynamic programming approach properly.
In fact, I would like to add something here.
Yeah, yeah.
So a couple of research papers have actually suggested that if we just introduce weight as a token explicitly between the think tags on a random basis, it actually improves reasoning. So
Oh,
certain
so
explicit
elaborate how?
so let's say the model is generating thinking tags, right? So basically, by introducing when the model sees weight as a token, it basically uh, it has learned to go into a divergent chain of thought, because that's when
Right,
we as humans also make a sense of the word weight when we are thinking
right,
about something. And
right.
this is exactly what they saw was happening with these LLMs as well. So exactly, so when they explicitly added this weight token, they could actually increase the number of thinking tokens significantly and thereby improve reasoning towards obtaining the final objective. And it actually helped.
Hmm.
So just a simple strategy can help. And and this is only during the inference time. This
So
need not
are
be
you
done.
are you saying whenever the model was outputting weight in their thinking token, they would increase the number of tokens limit?
No, no, no.
Okay,
I mean, so maximum number of the token limit you already set before doing the inference part, right? So
right,
it's so in some cases it might happen that the model is generating a lot of thinking tags, but it's still not getting towards a solution. So
right.
what introducing weight token it does it forces the model to explore divergent ways of thinking,
Okay.
thereby uh,
Oh,
kind
you're
of
saying they would introduce weight tokens.
exactly they would just
Oh,
introduce
okay.
weight tokens during inference time, and just
Got it.
that happened,
In
and
the
this was
during the
actually
thinking process.
yes, exactly.
Okay, so basically derail the model or basically cue the model to wait and possibly introspect and then go on a alternative path.
That's exactly right. And
Oh,
no
okay.
training was needed to do that. And it was actually inspired by this
Hmm.
aha moment of
Very
DeepSeek.
interesting. Very interesting.
Indeed. Yeah.
And did they achieve, like in the other paper that you're mentioning, did they achieve good results out of that?
Yes, yes, yes. They saw some performance improvements. I'm not exactly
Wow.
sure of the numbers, but I'll share that with you.
Great. Great. Yeah, yeah. Let's
Yeah,
share.
yeah, yeah.
Amazing insight. Cool. So those self-reflections and aha moments were there. And when they compared against the SWE bench verified by the evaluation setup we were discussing in the previous
Yeah.
like 2 slides back, they found that their RL-based model, like this paper, was performing or able to solve 41% of the use cases, much better than GPT-4o, Claude 3.5 Sonnet, and different scaffolds. And I think if I even compare with this, it was comparable to O1 Preview and DeepSeek V3 and poorer than 3.5 Sonnet with different scaffolds. Scaffolds is basically the agentic architecture that they were using, and DeepSeek R1 was better. And Claude 3.5
Interesting.
Sonnet with agentless or open hands was better. Yeah, so basically scaffold is also very important. So in this case, also possibly scaffold of agentless mini, which they used, could improve further. Like they could improve using just this. Otherwise, if we compare the base models, um, it's
It's
able to
significantly
perform pretty
better.
comparable. Yeah,
And with much few parameters as well. So just 70
right.
billion here, while GPT-4o and O1 style of models would have more than 1 trillion parameters
Possibly,
easily.
yeah. Yep. Not sure about 4.0 today, but of course, DeepSeek V3, so we know like 671 billion.
Yeah,
So, 10 times smaller
very
and
interesting.
still able to do it. Yeah. And compared to these Sui Llamas, 13 billions and all, so much better, 40 times better than this one.
Mhm.
33%
Wow.
better than Sui Fixer.
So it will be interesting to do this experiment on smaller models like Llama 7B or Llama 13B to see,
Yeah,
to actually gauge the impact of model
right,
sizes
right,
with reinforcement.
right.
Mm.
Yeah, yeah. Like we can pick it, or basically let's create this experiment internally and see if we can pick it. But and we could compare. Like, of course, they pick the best tool in their arsenal and try to get things forward. But
Yeah,
given the development that they have made, we can possibly repeat it with the Llama 7B
yeah.
and try to get things done.
Mm. Interesting.
Very interesting. Right. And one thing was that, as I said, that they were also comparing with the SFT benchmark. And when they were comparing the SFT is basically this entire data set they just did supervised fine tuning over a Llama 70 being struck with the greedy decoding. They saw that the correct format was better with SFT, as expected. The repair performance was better with RL. So saying that with
That
SFT
makes
also it was
sense.
not bad. Yeah, it
Yeah.
makes sense. But with SFT also though it was not bad. It was touching 30.
Mhm.
2 times what this Llama Instruct was doing, and so much better than the Llama uh, Instruct without majority voting. Majority voting was that they were doing a 20 sample majority voting result.
Again, an
Uh,
interesting experiment over here can be to take this up, Llama 3 SWE-SFT 70B, and then during the inference time, possibly introduce weight tokens randomly to see if that
right.
actually helps to improve the performance.
The SFT one or the RL one?
The SFT one, because we see that it's
But
already
SFT wouldn't be doing thinking. SFT would be directly doing prediction.
agreed. But given the fact that it is able to achieve a reasonably good repair performance, it it implies that it is doing some level of thinking within it, right? So even if it's not
Let's
within the
go.
thinking tag,
Let's check. Like, is SFT doing something under the thinking tags? Let's look at the paper if SFT is
no,
doing that.
it might not be doing explicitly within the thinking tags,
Mhm.
but just the normal output that is the normal tokens that are being generated. Because if I randomly introduce weight token uh, during inference, it will still impact uh, the prediction of the next token, right?
Hmm.
So even
Hmm.
not within the thinking tag, it can still have a non-trivial impact.
So it says that they supervised fine tune using synthetic data with COT. So it might actually be doing some kind of
Yes,
thinking. So weight
thinking.
tokens
Yes,
might help there. I
yes.
would be apprehensive if there was no thinking at all. I wouldn't put the weight tokens. But given that they're putting some weight tokens, it helps. And this
Mm.
is very
Yeah.
similar to the results that we have seen. We have seen
Okay.
that SFT on COT is
Uh-huh.
able to give comparable results and sometimes even better results than RL. So, the verdict is still out whether just reward-based RL, like reward-based RL is definitely helpful when you have a um, verifiable objective and less data. But if you have enough data and if you can create COT data, even SFT, a base model on that could be a stabler approach and a very accurate approach.
But here is one thing, right? So, uh, how about running SFT? Exactly what Deep Sea Carbon did, right? So they used this cold start principle where they did annotation of chain of thinking for a few samples, and then for the others, they simply trained on using RL technique. So for Genloop's experiment also, it might be worthwhile to first do SFT and then also augment it with RL for a few iterations.
Actually, we did that. So, of course, we're going to write a blog on that. But we didn't see much advantage of that.
Okay,
So, when
interesting.
we did COT SFT on 1,000, 2,000 steps, and after that we did GRPO, maybe the model accuracy was saturated in this case. So basically, that was the best oracle, like 71% was the best oracle with the particular problem that we had. The model was not able to do any better.
And this was
So
the
maybe if it
classification problem, right? HSN, if
Yeah.
I'm not wrong.
HSN
Okay.
classification. Yes, yes.
Okay.
So you remember, like with the HSN classification, after 2000 steps, we applied the GRPO reward based training
Yes.
again. And
Yes.
the accuracy, there was no delta in accuracy, 1% probably, and that is in the margin of error.
Okay. Okay. Interesting.
So verdict is still out. Possibly SFT and then reward modeling might help, or directly SFT can help. But these are definitely certain techniques to try out. Like I wouldn't rule out SFT on COT
Yeah. Yeah.
even after this
But that,
experiment.
anyways, is very important, as anyways mentioned by Deep Sea
Yeah.
Carbon.
Yeah, and that is how they created the distant model. The distant
Yes.
model was completely created by doing COT on SFT.
Yes. Yes.
COT on SFT is basically chain of thought based data and supervised fine tuning on that. Just for clarity to everyone. Right, and to the final uh, cherry on the cake, we saw that it was able to generalize even to other tasks. So what we've seen is when we do SFT, the model is basically doing behavior cloning and also trying to develop certain amount of reasoning, not very thorough reasoning. So it gets better at the defined task, but drops in accuracy in other tasks. That is something similar that we are seeing here. So with
Yeah.
function coding, a drop in accuracy compared to the instruct model. With the library use, which is not exactly it is trained on, the SFT is dropping accuracy. With code
Mm.
reasoning, it is getting better, much better.
Yep.
But with math, it's again dropping. For strict one,
Mm.
lenient ones is roughly the same. And for general, it's dropping. But the RL one, it's doing better than the instruct model, much better in terms of function coding, similar in library use, much better in code reasoning, even better than VSFT. Math, much better. So much better in math reasoning
Yeah.
compared to the instruct model, and general also better than the instruct model. So basically you're seeing this reasoning helps other tasks as well, and that is something that we can draw a human parallel also. Once someone learns reasoning, or let's say for coding, if someone is learning to code or learns coding, uh, they get their reasoning skills improve and they can apply it to multiple other domains like maths or logical arguments and all that, logical reasoning, data analytics and all that, and perform better compared to someone who's basically mimicking reasoning, but not exactly thoroughly understanding how to do things.
Yeah.
Right. So, conclusions and limitations. reinforcement learning is definitely a key choice to enable reasoning in LMs, even in software engineering or other domains. The learned reasoning helped generalize to various domains. SFT would not. But another point I would add here is too early to rule out SFT on COT based data set. And one limitation is, as we were discussing earlier, the reward models are not optimal. The agent scaffolding is not optimal. So there could be a lot of software engineering to create better, agentic scaffolding. Basically, seeing like multiple integrations of agents that could give it the right context of code and do things better, and definitely better reward models that could teach it, deeper reasoning and not make it stick to a certain style of change. Right. Any comments or anything to conclude from you folks?
Um, This was really good. I mean, uh, I enjoyed it at personal level quite a bit.
Right, right. No, that is where this research jam will be helpful.
Yeah.
1 hour every week or every other week, we'll see the cadence
Yeah.
to just take the best paper we have in an LM research hub and go over it, discuss it and get new insights on what other projects we could do. So I think do take a note of the two projects that you mentioned. Like those experiments could be something that we prioritize.
Yeah.
So just note it down somewhere or send it to me, and then I'll put it in
Yeah.
our roadmap.
I just write the minutes of this uh, research jam. I'll send it over.
Perfect. Cool. Thank you so much, everyone. Lovely start. And do share your feedback. If there's anything like we can improve on, do share the feedback for the next papers that we should cover. And hope to see um, mutual value in the next session. Thank you.
Yeah.
Ciao.
Thank you.
Awesome.
Bye bye.
Thank you.